Welcome to channel 360. Today our topic is forensic ballistics. Let's start the video. Forensic ballistics, solving crimes through bullets and firearms. Forensic ballistics is a scientific discipline that uses the analysis of firearms, bullets, and cartridge cases to connect evidence to crimes. This presentation will explore the principles, techniques, and advancements in this vital field, highlighting its role in solving various criminal cases. What is forensic ballistics? Definition: forensic ballistics examines firearms, bullets, and cartridge cases to link them to crimes. Key goals: to identify weapons, reconstruct shootings, and connect suspects to crime scenes. Forensic ballistics examines firearms and ammunition to link weapons to crimes by analyzing internal, discharge processes, external, bullet trajectory, and terminal, impact effects, ballistics. Experts compare microscopic tool marks on bullets/casings to specific firearms using comparison microscopes, while gunshot residue patterns estimate firing distance. Systems like IBIS cross-reference ballistic data globally, connecting cases. This field solves shootings, distinguishes suicides from homicides, and exonerates the innocent. Challenges include subjective tool mark interpretation, barrel wear altering marks, and debates over method reliability. Merging physics, engineering, and criminology, it delivers critical evidence for justice, despite scrutiny over forensic validity. Key applications: reconstructing crime scenes by analyzing trajectory and distance of bullets. Matching bullets and casings to specific firearms, identifying the weapon used. Identifying modifications made to weapons that are illegal, revealing intent or origin. Solving cold cases by searching ballistic databases for matches to unsolved crimes. Forensic ballistics aids criminal investigations by linking bullets or casings to specific firearms via tool mark analysis, solving homicides and assaults. It distinguishes suicides from homicides using gunshot residue, GSR, patterns and firing distance estimation. Ballistic databases, example IBIS, connect crimes globally by cross-referencing evidence. The field exonerates innocents by disproving suspect weapon involvement and reconstructs shooting scenes to determine trajectories, shooter positions, and bullet behavior. It also combats illegal firearms trafficking by tracing weapon origins via ballistic fingerprints. These applications provide critical, scientific evidence for court testimony, ensuring accountability and justice in firearm-related crimes. Now talk about types of ballistics. Internal ballistics. The study of how a firearm operates, including its barrel, rifling, and ignition process. External ballistics. Analyzing the bullet's path in flight, including its trajectory, velocity, and spin. Terminal ballistics. Investigating the impact of the bullet on a target, including wound patterns, penetration, and exit points. Internal ballistics examines processes inside a firearm during discharge, including primer ignition, propellant combustion, and bullet acceleration through the barrel. Rifling, spiral grooves, impart spin for stability, leaving unique marks on bullets used for forensic matching. External ballistics studies the bullet's flight path, influenced by velocity, gravity, air resistance, wind, and spin. Trajectory analysis helps reconstruct shooting angles and shooter positions. Terminal ballistics focuses on bullet impact effects, penetration depth, tissue damage, wound ballistics, and deformation. It determines entry/exit wounds, firing distance via gunshot residue patterns, and bullet behavior in materials, example glass, bone. Together, these disciplines aid crime scene reconstruction, linking weapons to injuries, and validating shooter/testimony accounts, crucial for forensic accuracy. The ballistics analysis process. Evidence collection. Careful recovery of bullets, casings, and firearms from crime scenes. Microscopic comparison. Matching striations, rifling marks, left on bullets and casings to link them to a specific firearm. Trajectory analysis. Using lasers, photography, and math to map the bullet's trajectory and calculate its origin. Database search. Using NIBIN, National Integrated Ballistic Information Network, to search for matches to other crimes. The ballistic analysis process begins with evidence collection, where bullets, cartridge casings, and firearms are meticulously recovered from crime scenes using gloves and sterile tools to avoid contamination. Next, microscopic comparison employs a comparison microscope to analyze striations, rifling marks, on bullets and breech or firing pin impressions on casings, matching them to a specific firearm's unique tool marks. Trajectory analysis reconstructs the bullet's path using lasers, trajectory rods, or software to calculate angles, origin points, and shooter positions based on impact sites and environmental factors. Finally, database search leverages systems like NIBIN, National Integrated Ballistic Information Network, which digitizes and cross-references ballistic evidence nationwide to link crimes or identify repeat offenders. This process solves shootings, connects cases across jurisdictions, and validates witness accounts. Challenges include degraded evidence, subjective mark interpretation, and database limitations. Together, these steps transform ballistic artifacts into actionable intelligence, bridging science and justice to hold shooters accountable. Let's have a short look into tools and technology for forensic ballistics. First is comparison microscopes. Side-by-side analysis of bullets and casings to identify matching striations. Second is NIBIN, National Integrated Ballistic Information Network, a database used to link crimes by comparing ballistic evidence from different cases. Third is 3D imaging. Creates virtual reconstructions of bullet trajectories, allowing for accurate analysis and visualizations. Forensic ballistics employs advanced tools to link firearms to crimes. Comparison microscopes enable side-by-side analysis of bullets and casings, revealing microscopic striations from barrel rifling or breech marks unique to specific guns, critical for confirming matches. NIBIN, National Integrated Ballistic Information Network, automates this process by digitizing ballistic evidence into a national database, cross-referencing marks from unsolved crimes to identify patterns, repeat offenders, or connected cases across jurisdictions. Meanwhile, 3D imaging reconstructs shooting scenes by mapping bullet trajectories through virtual models, accounting for angles, distances, and environmental factors, example wind, obstructions. This technology visualizes complex paths, aiding courtroom presentations and validating witness accounts. Together, these tools enhance accuracy, microscopes provide physical evidence, NIBIN uncovers broader criminal networks, and 3D imaging clarifies spatial dynamics. Challenges include database gaps, not all agencies use NIBIN, subjective mark interpretation, and resource-intensive imaging. However, their integration strengthens forensic rigor, turning ballistic artifacts into actionable intelligence for solving shootings, exonerating the innocent, and advancing justice through science-driven clarity. Let's see some of the challenges and limitations. Bullet fragmentation or deformation can make matching difficult. Lack of standardized ballistic databases globally, hindering international investigations. Subjective interpretation of striation marks by different examiners can lead to inconsistencies. Illegal ghost guns lack serial numbers, making them untraceable. Forensic ballistics faces significant challenges, including the subjectivity of tool mark analysis, where examiners' interpretations of striations on bullets or casings can vary, risking inconsistent conclusions. Degraded evidence from barrel wear, environmental damage, or corroded firearms further complicates matching. Databases like NIBIN are limited by incomplete data submission and jurisdictional gaps, reducing their effectiveness in linking cross-border crimes. Mass-produced firearms may share similar tool marks, causing false positives, while emerging technologies like 3D printed guns evade traditional ballistic fingerprints. Legal scrutiny questions the discipline's scientific validity, citing error rates and lack of universal standards. Resource constraints hinder access to advanced tools, example 3D imaging, and human error or cognitive bias may skew results. Additionally, evolving firearm technology reduces unique identifiers, challenging traditional methods. These limitations underscore the need for standardized protocols, improved databases, and ongoing research to enhance reliability and maintain judicial trust in ballistic evidence. Let's discuss some of the cases from the history for better understandings of forensic ballistics' importance as case studies. First case is famous as St. Valentine's Day Massacre, 1929. The first major use of ballistic evidence in a high-profile case. The 1929 St. Valentine's Day Massacre, where 7 members of Chicago's North Side Gang were executed by rival mobsters, marked the first high-profile use of forensic ballistics in U.S. history. After the shooting, police recovered over 70 spent .45 caliber Thompson submachine gun casings and bullets. Forensic pioneer Dr. Calvin Goddard used a comparison microscope, a then novel tool, to analyze the striations, rifling marks, on bullets and breech impressions on casings. His analysis confirmed all bullets were fired from 2 Thompson guns. Shockingly, the weapons were traced to the Chicago Police Department, stolen by Al Capone's gang. Though Capone avoided direct prosecution for the massacre, the case validated ballistics as scientific evidence, exposing organized crimes tactics and spurring forensic advancements. Goddard's work set legal precedents, proving firearms leave unique, identifiable marks, a cornerstone of modern ballistics. This case revolutionized crime solving, blending science and law enforcement to combat increasingly sophisticated criminal networks. Second famous case is known as DC Sniper Case, 2002. Nabin linked multiple shootings to a single rifle, leading to the capture of the perpetrators. The 2002 DC sniper attacks, carried out by John Allen Muhammad and Lee Boyd Malvo, terrorized the Washington, D.C. area with 10 deaths and 3 injuries. Investigators recovered .223 caliber shell casings from multiple scenes, analyzed via NIBIN, National Integrated Ballistic Information Network. The system matched the casing's breech marks to a single Bushmaster XM15 rifle, confirming a lone weapon linked all shootings. This critical insight unified the sprawling investigation, disproving initial theories of multiple shooters. Ballistic evidence traced the rifle to Muhammad, whose blue Chevrolet Caprice, modified for covert shooting, was later found. Combined with eyewitness accounts and cell tower data, Nabin's matches solidified the connection, leading to their arrest. The case highlighted Nabin's value in linking serial crimes and prioritizing suspects, while exposing gaps in real-time data sharing. It spurred reforms to accelerate ballistic database integration, ensuring faster identification of ballistic fingerprints in future cases. Third case is famous as John Dillinger's death, 1934. Ballistic analysis confirmed the FBI's claim that Dillinger was killed in a shootout. The FBI's claim that notorious bank robber John Dillinger was killed in a 1934 shootout outside Chicago's Biograph Theater was validated through ballistic analysis, quashing persistent survival myths. After Dillinger was shot, agents recovered bullets from his body and the scene. Using comparison microscopes, examiners matched the rifling patterns on the bullets to the .45 caliber Colt pistols carried by FBI agents, confirming their weapons fired the fatal shots. This analysis aligned with autopsy findings: 3 bullets struck Dillinger, 2 fatally piercing his heart and brain. Despite conspiracy theories, example a lookalike died in his place, the ballistic evidence, combined with fingerprints and eyewitness accounts, solidified the identification. The case underscored early forensic ballistics' role in legitimizing law enforcement narratives and dispelling public skepticism. It also highlighted the FBI's growing scientific rigor under J. Edgar Hoover, setting precedents for evidence-based accountability in high-profile cases. Dillinger's death marked a turning point, proving even legendary outlaws could not escape the reach of forensic scrutiny. Advances and future trends. Automated systems. Artificial intelligence, AI, is being developed to speed up striation matching. Microstamping. Etching unique serial numbers on bullets and casings for easier identification. International collaboration. Sharing ballistic databases across countries to improve global investigations. Recent advancements include 3D imaging for precise bullet trajectory mapping and automated systems, NIBIN, to link crimes via ballistic databases. AI tools now analyze tool marks faster, reducing human bias. Future trends focus on micro-CT scanning for ultra-detailed bullet scans, blockchain to secure evidence chains, and global databases for cross-border crime solving. Challenges like 3D printed guns, leaving no traditional marks, push innovation in non-traditional ballistic tracking. Labs are adopting machine learning to predict firearm types from fragmentary evidence. However, standardizing methods, updating laws, and balancing speed with accuracy remain hurdles. The field aims to enhance precision, collaboration, and adaptability against evolving weapon tech. Conclusion and ethical considerations. Forensic ballistics plays a crucial role in solving gun-related crimes. Rigorous standards are essential to ensure accuracy and fairness. Future directions include tackling ghost guns and enhancing international data sharing. Forensic ballistics is indispensable in solving firearm-related crimes, providing critical links between weapons, suspects, and victims. However, its efficacy hinges on rigorous scientific standards to ensure accuracy, minimize human bias in tool mark analysis, and uphold judicial fairness. Ethical concerns include privacy risks from expanding ballistic databases and potential misuse of genetic data in familial searches. Future challenges demand addressing ghost guns, untraceable, homemade firearms, through advanced tracking methods and harmonizing international data sharing protocols to combat transnational gun trafficking. Innovations like AI-driven analysis and 3D imaging must balance efficiency with transparency to maintain public trust. Strengthening global collaboration and modernizing legal frameworks will be key to adapting to evolving technologies while safeguarding civil liberties. By merging scientific rigor with ethical accountability, forensic ballistics can continue advancing justice in an increasingly complex world.